Hi, everybody. It's April 16th, 2020. Um, we are about a month into the coronavirus shutdown, and I am giving a talk about a deep learning project that I did at home. And I'm doing it partly because it's not possible to give talks to a group of people at the moment. Um, so today there's news that remdesivir from Gilead Science looks promising. So let's hope that works out and we can get back to our normal routine soon. um, so in the first part of the talk, I gave introductory material, and now I'm going to get into the heart of the talk. And let's go ahead. I'm sharing the screen, and these are my slides. Okay, repeating just a little bit from the first talk. And by the way, I'll try to make it so that it's easy to find one talk from the other. The first talk was really background. I explained a lot of the terminology that I'm using. And this talk, I'm going to get more into the work itself. So this talk is about using deep learning to try to solve the phase problem for a simplified case. And by that, I mean training on neural network input, where the network inputs are diffraction data, or in this case, I'm using Patterson maps, which are a kind of a simple transformation of the diffraction data. And then on the outputs, I'm training on atomic coordinates, or really electron density maps, or kind of simplified electron density maps. So the idea is to go from the data that's collected during an X-ray diffraction experiment and see if the network can learn to determine what the electron density map looks like directly from the X-ray diffraction data. This work is a personal project. These opinions that I'm expressing here are my own. I work at the NIH, but this work does not reflect the view of the NIH, Department of Health and Human Services, or the United States government. So this was just strictly a personal project because I wanted to acquaint myself with and practice using deep learning methods. I've put a paper about this work on arXiv, and here is a link to that arXiv paper. This is the outline for the talk. First, in the first video that I made, I gave introductory material about the phase problem, what a Patterson map is, what a neural network is, what a convolutional neural network is. All this introductory material is covered in the first talk. And now for this second talk, I'm going to talk about the work itself, methods, results, and conclusions. So I'm skipping ahead now to the methods section. Okay. Before I start on the methods section, just let me give just a little bit of background, which is to say that this neural network problem that I'm working on is actually the second deep learning problem that I worked on. Second home deep learning project that I worked on. The first one, what I tried to do was use a neural network to run a molecular dynamics simulation. So I trained it on a lot of molecular dynamics simulations with long trajectories, and I saw if the network could basically learn to take the next step in a molecular dynamics trajectory. And I had some success with that. It can do a short number of steps, but it can't really continue the trajectory going for a lot of steps. But anyway, so when I got bogged down in that, I thought, well, let me see if I can basically take what I have and borrow some of it, and rather than use atomic coordinates on the input and atomic coordinates on the output, use atomic coordinates on the output, and then from that, calculate diffraction data that's sort of synthetic diffraction data, and then put that on the network input, and in that way to see if the network can go from X-ray diffraction data to atomic coordinates, and thereby you essentially doing direct methods in X-ray crystallography. So one other point I want to make is that, I know that I've heard other people have said that they think that deep learning could be applied to this problem. And I independently think that as well. And as far as I know, I haven't seen any papers on using neural networks to solve the phase problem. And I believe this to be original work, an original deep learning project on a new application. Okay, so now an overview of the methods. On the output, I'm creating kind of a simplified electron density map for 10 atoms. Then I'm calculating a Patterson map from that simplified electron density map that's on the output, and that goes on the input. Then I train on tens of thousands of these training cases where I show it a Patterson map, and I basically tell the network, this is the atomic configuration for this Patterson map, and over and over and over, and then try to see if it can not only train on that data, but also generalize to cases that were not in the test set. So one observation is that input and output are images. The Patterson map is has real physical meaning, and it's in real space, not Fourier space. And by having input and output images, this method lends itself to convolutional neural networks. And also another observation that this is a deconvolution problem, and that some deconvolution problems have been, neural networks have been applied to some deconvolution problems, like image super resolution, also called image sharpening. And what I mean by it being a deconvolution problem is that the input image, namely the Patterson map, is a convolution of the electron density map with its inverse. And so if the input image is a convolution of the density map with itself, then, and I'm going to the original electron density map, that is a kind of deconvolution. Okay. So now regarding the output data representation. So as I said, this work started out because I was training a neural network to run a molecular dynamics simulation. And at that point, I wasn't really interested in making any kind of realistic electron density map. Rather, what I was trying to do was just make a simplified electron density map to encode where the atoms were located in a grid. And so this is the way that I was doing that, is to basically choose a well, in this case, I'm choosing random atom positions. So this is the way it would work. Choose a random atom position and then create a sphere around that random atom position, a sphere whose radius is 1 pixel length. So therefore, this one atom position is then encoded in up to 27 pixels, the pixel where the atom itself resides and the neighboring pixels. In practice, it turns out that roughly 20 pixels are involved in encoding each atom position. And so then what you can do is look at the pixel itself and all of the neighboring pixels and calculate what fraction of the pixel or voxel, if you're working in 3 dimensions, what fraction of the voxel is occupied by the sphere. And that's the value that's assigned to each of these pixels, the pixel where the atom is located and the neighboring pixels. So in this example, the 1.00 means that this entire voxel is occupied by the sphere. And then you look here where it says 0.71. Well, this pixel is mostly occupied by the sphere, and like that. And then during the inference stage, you can use this information to determine a more precise location for the atom position than just the pixel itself. So what you can do is then take a weighted average of the pixel and its neighbors weighted by these fractions to get a more precise location for where the pixel is located. And that works fairly well, like because you're involving 20 or so pixels, you're getting something like an accuracy that's 20 times better than just using the pixel itself. Okay, so why not use synthetic density? Well, I addressed that, but I'll just say that in future work, I would use synthetic density, or make density maps that are more accurate or better models of electron density. And okay, well that's that. That's the output data representation. So now the input data representation. So once that electron density is calculated, once the electron density map is calculated for the network output, then you can make a Patterson map from that density map. And it's pretty straightforward how to do it. You take the Fourier transform of the electron density, multiply it by the complex conjugate of the Fourier transform, and then take the inverse Fourier transform of the product. That's that second equation that I'm showing you here. So essentially what you're doing is you're squaring all of the Fourier terms and then taking the inverse Fourier transform, and that gives you the Patterson map. And because of the convolution theorem, this is mathematically equivalent to doing a convolution in real space. So in other words, convolution in real space is equivalent to a multiplication in Fourier space. So in real space, what this is equivalent to is taking the electron density map, convolving it with the inverse of the electron density map. But in practice, this is the way to do it. It's a fast way to do it because you can use the fast Fourier transforms. And a Patterson map has a real physical meaning. So whereas in the electron density map, there will be n peaks for each of the n atoms that are represented by the electron density map. In the Patterson map, there are n times n minus 1 peaks, or roughly n squared peaks, where each peak corresponds to a vector between each pair of atoms in the electron density map. So if you were to make a list of the pairs of atoms in the electron density map, there would be roughly n squared pairs of atoms, and then if you consider a vector between each pair of atoms, that's what is represented in the Patterson map. The Patterson map has a peak for each vector, each vector between each pair of atoms in the density map. And that goes on the neural network input. Okay, a little bit about the network architecture. The network architecture that I use is very simple. It just consists of 12 3D convolutional layers, where each layer is either 5 by 5 by 5 or 7 by 7 by 7 kernels, where each of the convolutional layers is uses either 5 by 5 by 5 or 7 by 7 by 7 kernels. There's one max pooling layer and one upsampling layer. I'm going to go to the, I'm going to come back to this in a second, but I'm going to go to the schematic because in some ways it's easier to explain here. So there are these horizontal arrows represent convolutional layers. The down arrow is a down sampling layer. In this case, a max pooling layer, which reduces the number of pixels from the original number, 40 by 40 by 40 in my case, down to 20 by 20 by 20 pixels. It does that by considering every group of 8 pixels and selecting one of them. It's a simple method for reducing the resolution of the image. And then there's one upsampling layer, which goes from the low resolution back to the higher resolution. And by the way, these are all common neural network layers that are used here. And at the higher resolution, I'm using 5 by 5 by 5 convolution layers. And at the lower resolution, I'm using 7 by 7 by 7 convolutional layers. And then you see on the input is the Patterson map. That's one channel. And on the output is the density map. And that's one channel. And all of these 20s here above the vertical bars are the number of channels at each of the internal layers. So it's really the number of kernels that are used at each of the internal layers. Okay, going back here to the description of the network. So I mentioned earlier that I had very sparse data on the neural network output. And what I found was that the training did not go well if I used batch normalization layers. In fact, even if I used batch normalizations in the early convolutional layers, it seemed to mess up the output of the training. So I found when I got rid of the batch normalization layers that the training went better. And that's one reason that I wanted to use a relatively low number of convolutional layers, and also one reason for doing the downsampling and the upsampling is because you can get a big receptive field that way, larger than the receptive field gains that you'll get at the high resolution layers. And also why I use the 7x7x7 kernels at the low resolution layers. So input and output dimensions are 40 by 40 by 40. The receptive field turns out to be 56, which is good because since you're doing a Fourier transform, you want the output pixel, each output pixel needs to basically feel each input pixel. And so that means that the receptive field has to be at least as big as the dimension, this 40 by 40 dimension of the image. And that was also a consideration. The number of weights works out to be 1.2 million. I use Keras for building, training, and running the network, and that went well, and it's very simple and easy to use. And I used a home gaming computer with an NVIDIA GTX 1080 Ti GPU for accelerating training and inference. And just one thing I noticed was that when I didn't use the GPU, the training went about 150 times slower than when I did use it. So obviously huge performance gains going to the GPUs. All right, so that's a basic idea of the network architecture. And here's a code snippet that shows, really how simple it is using Keras to encode that architecture. And you can see here there's 12 3D convolutional layers, one max pooling layer, one upsampling layer. At the lower resolution, there are 8 convolutional layers, and then 2 preceding that and 2 after that at the higher resolution. The 5 here means 5 by 5 by 5 kernel. The 7 is obviously 7 by 7 by 7 kernel. The 20 means that there's 20 channels on this layer's output. I was using ReLU activations. And yeah, so that's it, a kind of simple code snippet. And it makes it easy to work with the networks that way. All right, now I'm getting to what I consider the very important part of this talk, which is the important considerations for training the network. And this is the key thing. The network cannot train on conflicting data. And so what I mean by that is, so consider a classifier network where, let's say you have thousands and thousands of images that you're training on, and you're showing the network cats and dogs and horses and so on. And so let's say you present the neural network input with an image of a cat. You say, here's a cat. Then you present it with a dog, and you say, here's a dog. And the network's training, and it's learning that. But if you were then to present the network with an image of a cat, that you had already presented to the network and identified it as a cat, and this time you present it again and you say, no, it's a dog, that will make it very difficult for the network to train. It will mess up the training. The network can't train on conflicting data. And if you give it conflicting data, it won't train and it won't generalize. And so in a very comparable way, you can't train on conflicting data for the phase problem either. You can't present the network on the input with a Patterson map and say, okay, this is the atom configuration that is paired with that on the output, and then give it the exact same Patterson map on the input and say, actually, not only does that Patterson map represent that arrangement of atoms, but it represents this arrangement of atoms as well. And if you do that, the network won't train. So there are three ways that this needs to be taken into account. And that's what I'm going to talk about now. Number one, the Patterson map is translation invariant. So what that means is that if you give the Patterson, or let's do it the other way around. If you have an atom configuration of atoms on the output and you calculate the Patterson map, then you take that configuration of atoms and you translate it in X, Y, or some kind of combination of X, Y, and Z, and then you calculate the Patterson map for that, you're going to have the same Patterson map. And that's a problem for training the network. So what you can do is simply take the output image and center it at the average position of the atoms in the output. So just calculate the average position of the atoms in the output and put that in the very center of the output image of the neural network, and always use that. And that takes care of that translation invariance. Okay, the second important consideration, is that the network is invariant to centrosymmetric inversion. So what does that mean? That means if you have a certain atom configuration of atoms and you calculate the Patterson map for it, and then you were to take the centrosymmetry operation, which I'll explain in a second what that is, but let's say you were to take the centrosymmetry related atoms and then calculate the Patterson map for that, it would be identical. And that's a problem for the network to train on. So in this case, all right, let me say what a centrosymmetry is. So imagine that you have atoms at like X, Y, X1, Y1, Z1, X2, Y2, Z2, and so on. So the centrosymmetry operation is just flip the signs on all of those X's and Y's and Z's. So rather than having the atoms at X1, Y1, Z1, and so on, you have atoms at minus X1, minus Y1, minus Z1. That's the centrosymmetry operation. You can think of it kind of like a mirror image, even though it's not really, but it's a centrosymmetry inversion. And a group of atoms, or an electron density that's made from a group of atoms, and an electron density that's made from the centrosymmetry of those same atoms, both have the same Patterson map. And you can't train on one and then the other, and there's really no way to distinguish one from the other. And so what I figured out to do was to train on both sets of atoms simultaneously. And that was kind of a key for getting this whole thing to work. So the way it works then is take the atoms, calculate electron density for it, calculate the Patterson map from that electron density, then take the original atoms, calculate centrosymmetric atoms from it, and calculate electron density from that, and then simply add the electron density from one to the electron density from the centrosymmetry operation, and that becomes the network output. I'm going to explain this more in the coming slides. And the third important consideration is that the Patterson map is actually ambiguous with regard to vector origins. So when you look at a vector in a Patterson map, or when you look at a peak in a Patterson map, it's not clear which origin of the cube the peak represents. And because of that ambiguity, the Patterson map is not unique. And if you could remove that, and this is even apart from the centrosymmetry and the translation invariance, if you could remove this ambiguity, then you can make it so that the network trains. I'm going to explain. Okay, number one, I think is fairly obvious what's meant by that. You just center the atoms in the output. But number two and number three are a little bit more involved, and I have some slides to explain that. Okay. So, as I said, the Patterson map is invariant to centrosymmetric inversion. So here's a configuration of atoms. These are its centrosymmetry related atoms. You can kind of see that it looks like a backwards image of it or something like that. You know, like these two here are these two here. These, this map and this map have the same Patterson map. And so the way that I've approached that is I take this density map, I calculate the Patterson map, that goes on the input. Then I calculate this density map, the centrosymmetry related density map, and I add these together, and that goes on the network output. I think I said that the Patterson map goes on the input, and this sum of density maps goes on the network output. And then the network can train. That was kind of a key finding to getting this whole thing to work. Okay. Now, what do I mean about the Patterson map being ambiguous with regard to vector origins? So let's say that here on the very left box, I have a Patterson map with 6 peaks. So there are 6 peaks in the Patterson map because there are 3 atoms, and 3 times 2 is 6. That's the number of peaks is n times n minus 1. But the question is, how do you draw the vectors here? So you see here is a set of 3 atoms, and here is a different set of 3 atoms. And if I create a Patterson map from each of these, the Patterson map will look like this in both cases. And the reason is that the vector origins for the peaks in the Patterson map are different for the 2 maps. So you can see, like, you see this vector between these 2 points? That's this vector here. Well, that's the same in both of them. But let's say this vector here, well, maybe it's a little bit hard to explain, but the point is that if you take these vectors here and move them to the origins, they will look like this. And if you take these vectors here and you move them to the origins, they will look like this. And actually, this Patterson map is the same as this Patterson map because the Patterson map doesn't have the lines. It only has the peaks. And it's not clear in these two maps where the origin is, where the origins are. But if you make it so that the vectors between the atoms are sufficiently small relative to the overall box dimension, then when you look at the Patterson map, it will be clear that each peak, it will be clear to which vector, to which corner of the cube, which corner of the cube is the origin for a particular peak, because there will only be one distance that is sufficiently small that it can be that vector. In other words, if all of these distances here are sufficiently small, and then you're trying to assign each of these points to an origin, it must be that the peak is assigned to the origin that it's closest to, because there are no vectors bigger than that in the collection of atoms. So I have one more picture that explains that. So I'll try to explain that again, because I know it's a little bit confusing. So if what you do is you confine the atoms in the output to a box within a box. So these are the 10 random atoms, and they're confined to a box within a box. So this is the distance across the inner box. And if you make it so that this distance across the inner box is half of the outer box edge dimension, then what it means is that all of the interatomic vectors have distances that are less than half of the box edge. Therefore, when you see a peak in the Patterson map, you know what the origin is for that peak. It has to be the origin to which it is closest, because the distance between this peak and any other origin is more than half of the edge length. And so then it becomes unambiguous which origin to use for every peak in the Patterson map. All right, so I hope that's clear. I'm going to continue on now. Okay, one more point about the centrosymmetry technique that I used is that, as I described it, I'm going to go back a couple of slides here. As I described it, you're taking electron density and electron density from the centrosymmetry atoms, and you're adding it together. And this is what you're training on. So what it means is that rather than training on 10 atoms, I'm training on 20 atoms, and I'm solving for 20 atoms all at the same time. So that creates a problem, because now I've solved for twice as many atoms as I want. And not only that, I don't know which, I don't know how to divide it up into two unique sets. I don't know where the dividing line is. And so those two sets of atoms have to become untangled. And so that's what I'm getting at here is now I'm going to describe a way to separate the combined atoms into two separate sets. So you see here, here's the Patterson map, train on twice as many atoms as you really want, and then post-processing, separate that into original atoms and centrosymmetry atoms. But there is a limitation to this method, which is that actually both of these solutions are equally valid. They both produce the same Patterson map. And so in the end, you'll end up with two solutions, and they're both reasonable solutions. But if you're solving for proteins at atomic resolution, say, then you should be able to figure out which is the correct model because of the chirality of the residues in the protein. And so it should be that the user can figure out which of these two will be correct. Okay, so how to do that? So the Patterson map can be used as a guide for separating these atoms into two sets. And the basic idea is that what you're trying to do is identify 10 atoms in here whose Patterson map matches the Patterson map that's on the neural network input. So you can calculate a Patterson map for any group of 10 atoms in here, and then compare it to the true Patterson map and select the one that's the closest. Now, for just 10 atoms, you could just enumerate all the possibilities. Well, I guess that would be a large number, but and then just take the one that's the closest. But actually, what I did was I used like a greedy algorithm, and I started out with just some collection of 10 atoms, and I calculated a Patterson map from it. And then I selected one of those atoms at random and swapped it out with one from the group of 20 that wasn't in the set of 10, and just made a swap and calculated the Patterson map, a new Patterson map. And if the Patterson map improved, then you keep the swap. And if the Patterson map got worse, then you reject the swap. And just by doing swaps like that, you can get the collection of atoms, the group of 10 atoms, to separate them into two sets. All right, here's the algorithm for it. I'm not going to go into it in detail, but the basic point was that what you're doing is you're looking for a group of 10 atoms whose Patterson map most closely is most similar to the true Patterson map. And you do atom swaps until you find one that's good enough. Yeah. All right, now I'm moving on to the results section. Okay. The training batch size was about 3,000, and I remade this every few epochs. So what I mean by that is that I would make 3,000 density maps, 3,000 corresponding Patterson maps, and train on that for a few epochs, and then discard that and do it again. Make another 3,000, train on it for a few epochs, and discard it. And that, then the validation batch size was only 100, I made that at the start of a run and used that exact same validation batch for the entire run. And by a run, what I mean is a continuous operation of the training without changing any parameters at all. But occasionally I would stop the run, or and then I would make small adjustments, not to the neural network itself, but to some training parameter like the learning rate, say, or the number of the size of the training batch, or some small adjustment like that. And then, so this trained for about 4,000 epochs over 26 different runs. It took close to 2 weeks to do the training. Each run took between a few hours and a few days, and hyperparameters were adjusted each run. Okay, so what this is showing is the loss function for the training in red and the validation in blue. And this is a good result because it is showing that as the network is training, the validation set, the loss for the validation set is decreasing in tandem with it. And that's an indication that the network is training and generalizing. And actually, if you look at the red here, like, I don't know, I said that I'm swapping in new data every few epochs. So even just the fact that the training curve is decreasing is an indication that it's generalizing, because every few epochs I'm swapping out all the data and I'm swapping in new data, and it's continuing on its good learning curve. So actually, the data doesn't look just like that. It looks like this. That's not the same scale, but that's what it looks like. Why does it look like that? I'm going to zoom in a little bit here and show you. That's the section I'm going to zoom in on. Okay, so look at the red, that's the training. And what's happening is, you see here at the top of one of those zigzags, you're getting a new set of training data. And then it trains on that for a few epochs, and then that's swapped out and a new training batch is swapped in. And so that's why this has that kind of zigzag character, because of the way that the training schedule is structured, that new data is swapped in every few epochs. And so going back here, the reason that the zigzags, you don't see them here, is that I've actually just filtered them out. So I'm taking the low of the few epochs to display here. But in reality, the training went like that. All right, so I did a couple of tests to see. So I've made the claim that earlier that the network won't train and it won't generalize unless you take care of the centrosymmetric atoms, and it won't train and it won't generalize unless you take care of this ambiguity over the vector origins of the Patterson map. So I did a couple of tests to see if that was really the case. So here's one test. So what I'm doing here is I'm using the same network and I'm training it from scratch, putting in random numbers and back into all of the weights, and then trying to train. And in the case of the dark red and the dark blue, that's training the way that I said works, which is to use the centros, the original atoms, and the density from the centrosymmetric atoms to train on both simultaneously. And you can see here that you see that's still zigzag. I'm using the same kind of training schedule, but that it's training in that the loss function is decreasing. And you can see also that it's generalizing because the dotted line represents the validation data, and that also is improving as the network learns. And so here in the light blue and the light purple colors, what I did is I removed the requirement that the centrosymmetric atoms, the density from the centrosymmetric atoms be used simultaneously in the output density map. And so in one case I'm training with 10 atoms, and in one case I'm and doing a small bit of scaling, and in one case I'm training with 20 atoms. And what you can see is that the network is not training nearly as well if it's training at all. So when you don't take into account of training on the atoms and the centrosymmetrically related atoms, the network does not train anywhere nearly as well as when you do take it into account. All right, now here's the second test that I did. This is the one where I'm considering a box inside of a box. And I was saying that what I did was I confined the 10 random atoms into a relatively small space inside of the overall output box. And so in this case, I'm relaxing that constraint. So this blue and purple are the same as the blue and purple from the previous slide. But now what I'm doing is I'm making the box that it's confined to a little bit bigger, and then a little bit bigger still. And so when I make it a little bit bigger, you can see that the training doesn't go as well. And when I make it bigger still, you can see that basically there's no training at all. And that is demonstrating that I think that you need this idea of the empty space around the atoms for training, so that the network can train without that ambiguity of where the vector origins are for the Patterson map. Now, whether you can do this with real data is open, an open question. That hasn't been done yet. Okay, now what I'm going to show is results from the inference stage. So in this case, what's going on is that the network has been trained and it's fixed. It's not changing anymore. And now I'm creating new atoms and density maps and training on those. I mean, I'm sorry, not training on those. I'm just creating the density map, creating the central symmetry of the density map, adding those together. And that's what you're seeing here. And I'm calculating a Patterson map from either one of those, the blue or the red, and putting that on the neural network input. So the Patterson map is put on the neural network input, and then we basically just see what output the network generates given a Patterson map that wasn't in the training set. This is what the true output looks like. And again, reiterating, the network did not train on this. And this is what the neural network output looks like during the inference stage. And I'm going to show 6 examples of this. And in each one, the neural network output looks remarkably like the true output. And and I looked at many more cases than that. I did this 500 times, and I looked at a lot of them, and they all look very, very similar to the true output. Each predicted output looks similar to the true output. So now I'm going to show the 6 of those. Okay, that's all 6 of them. And you can see the strong similarity between the true output and what the neural network is predicting as its output. So it seems to be inferring atomic coordinates, or at least density maps, from Patterson maps. Okay. So I mentioned that I had an algorithm to separate the combined density maps from 20 atoms now into 2 different sets. And what I'm showing here is the mean squared error between a calculated Patterson map from 10 of those atoms to the true Patterson map on the neural network input as the combination of 10 atoms in the set converges. So in other words, there's a set of 10. I'm selecting 10 of those at random, and then taking one at a time at random and swapping it out with one that's not in the set, and letting those swaps, keeping the swaps that improve the similarity between the calculated Patterson map and the true Patterson map, and rejecting the ones where the similarity gets worse. And you can see a little bit of up and down here. Actually, I didn't use a straight greedy algorithm. I used some simulated annealing, and then I just let that run for lots and lots of steps, and it worked quite well, as you'll see in the next slide. Okay, so now what I'm doing is I'm taking, this is kind of like a best case, because as I said before, you can't really distinguish one set from the other once you have the atoms and the centrosymmetric atoms. So I want to compare that to the true atom positions that were used to make the Patterson map. So what I'm doing here is I'm taking a set of 10 atoms and comparing it to the true atoms. And if the comparison is just horrible, then I'm saying, okay, let's not compare that set of 10 atoms. Let's compare the other set of 10 atoms. And then, so this is kind of like an idealized case. It's as if I know which set of 10 atoms is correct, even though I don't know which set of 10 atoms is correct. And then I do that position test for positional accuracy. Okay, so when I do that, I'm looking at the difference in position between the atom position that's derived from the output map of the neural network to the true atom position, and I'm looking at what the difference is in pixels. And this is what I found is that the average accuracy is 0.283 pixels. In other words, each atom position can be recovered down to sub-pixel accuracy. And the way, once you have the atoms, one thing that I mentioned early on in the talk, but I'm going to mention again, is that when you have the output density map, you can calculate an atom position using a pixel and its neighbors and doing a kind of weighted average of those pixels to get an atom position. And that's the position that's used to compare to the true atom position. So I said earlier, and I'll repeat that I did this 500 times with 10 atoms. So for a total of 5,000 atoms. But for only 6 atoms, no assignment could be made. In other words, it was ambiguous which atom in the output map corresponded to an input map atom, or vice versa. It was ambiguous which atom in the input map corresponded to the output map atom. But for 4,994 of the 5,000 atoms, the average accuracy was 0.283 pixels, with the caveat that I'm acting as if I know which of the 10 sets of which of the 2 sets of 10 atoms is the correct one. All right, so that's the end of the results section, and I just have this one conclusion slide, which is that I set out to see if I could train a neural network to infer density from Patterson maps, and it seems to be working quite well, at least for this small and simplified case. For a test set of 500 Patterson maps on which the network did not train, the neural network outputs closely resemble the density maps which were used to create the test set inputs. So I looked at many of those, of those 500 visually, and they were every one that I looked at was strikingly similar. And then I did that comparison to look at how closely the atom positions matched up, and that was quite good as well. With again, the given limitation that you can't tell atoms from centrosymmetry atoms on the output. For future work, what I would want to do is use actual, synthetic density maps for real molecules, and see if this method would work for larger structures, and importantly also see if this would work at lower resolution, because that could be really quite useful, because right now direct methods won't work unless you have atomic resolution. So if this could work at lower resolution, it would be valuable. And I think that's it, except for I want to say thanks to Fred Dita at the NIDDK. He is an X-ray crystallographer. He was very generous with his time with me. He gave me a lot of valuable insights about X-ray crystallography. I personally thought that I should put his name on the paper that I wrote, but he felt that he didn't make significant enough contributions to warrant that. But it was his idea to use Patterson maps on the neural network input, and that was a valuable contribution. So I'm very grateful to him for his help and insights. And that concludes the talk. Thank you.